an environment was sensed that would allow that signal to pass. So there was an open switch, literally, the first open switch for safety.
Sandia would address this problem and oversee the installation of environmental sensing devices in bombs and warheads throughout the stockpile. Comprehensive stockpile safety began with the work of the influential Klee Committee report that spawned nearly 70 safety studies, culminating in a Department of Defense directive establishing formal safety standards for nuclear weapon design.
The Klee Committee clearly influenced the future direction of safety, creating the positive measures. The positive measure concept was incredibly powerful in the sense of saying we need to see something that's engineered specifically for safety. Safety really means availability. If you have a safe weapon, you can deploy it anywhere in the world and not put the public at risk.
By 1960, SAC was running an operation called Positive Control Launch to ensure the survivability of its bombers. This deployment of nuclear-armed B-52s would present new challenges for detonation safety.
An atomic bomb breaks loose from a mounting shackle in a B-47 jet over Florence, South Carolina, plummets to Earth, causing a sensational freak accident.
A Mark VI gravity bomb, accidentally dropped by an Air Force bomber, was of the earliest generation of capsule-type weapons. No nuclear capsule was aboard the bomber or installed in the weapon, and damage was limited to the detonation of the bomb's high explosive. The accident in March 1958 was the 13th involving air-delivered nuclear weapons. 6 months later, the Strategic Air Command would begin to test its continuous airborne alert mission. During the next 10 years, the Air Force would be plagued by accidents involving air-delivered nuclear weapons.
We were running some fairly high-risk operations. We were flying a large number of airplanes and during most of the 50s and into the 60s, continuously with nuclear weapons on board.
Hardware wears out. Things happen. And the Air Force caught the brunt of those issues.
Their focus was reliability, readiness, not accident safety.
In the late 1950s, Strategic Air Command began to carry sealed pit weapons, where the bomb was loaded up and always ready to go. Accidents involving sealed pit weapons would represent a manifold change in the risks of an accidental nuclear detonation. One of the earliest accidents involving airborne alert bombers occurred in January 1961 over Goldsboro, North Carolina.
It was a normal flight. It had just refueled with a KC-135 tanker. The boom operator on the KC-135 told the pilot that he noticed a pink fluid leaking out of the right wing of the airplane. Pilot disengaged, radioed in to SAC headquarters to say that he had a fuel leak. B-52s are a big flying fuel tank, and it's necessary so that they stay in the air. You've got to transfer fuel from the center body of the aircraft out to the wings. During one of these transfer operations, the right wing of the airplane physically ripped off. All of a sudden, now that weapon system is free. As the weapon dropped, power was now coming on, and the arming rods had been pulled, the barrel switches began to operate. The next thing in the timing sequence was for the parachute to deploy. When it hit the ground, it tried to fire.
There was still one safety device that had not operated, and that one safety device was the pre-arming switch, which is operated normally by a 28-volt signal.
Some people can say, hey, the bomb worked exactly like designed. Others can say, all but one switch operated. Not one switch prevented the nuclear detonation.
Unfortunately, there have been 30-some incidents where the Ready Safe switch was operated inadvertently. We're fortunate that the weapons involved at Goldsboro were not suffering from that same malady.
The accidents provided valuable information to AEC weapon designers. At Sandia, improvements were made in later generation pre-arming Ready Safe switches. Unfortunately, there was no shortage of new data as the accidents continued. In January 1966, a mid-air collision over southern Spain raised international alarm.
The accident over Palomares, I think, was significant because of the scattering of plutonium on foreign soil. It had incredible press coverage of that arena and incredible negotiation between the U.S. government and the Spanish government with respect to the level of cleanup.
We wound up buying up a lot of tomato fields over there. After the accidents, many things became more evident to us and in fact to the world, because it was such a stage that they could see now.
The U.S. was embarrassed in a world community.
In early 1966, Strategic Air Command's Airborne Alert Mission, codenamed Chrome Dome, had been operational for 5 years.
Robert McNamara, who had been skeptical about whether the Chrome Dome operation was still necessary, wanted to put an end to it. Strategic Air Command was able to argue that that was a very rare event, it won't happen again, we've instituted operational procedures so that there won't be another accident of that sort. Unfortunately, they were wrong. B-52 on an airborne alert mission had a fire on board. The aircraft crew evacuated the aircraft. The plane then drifted without anyone on board, landing 7 miles outside the base, blowing up on the ice.
When the plane went down, it tended to melt the ice and then plate the thing, so you had a layer of ice over the top of the contamination. They had about 39 inches of ice when we got there, and of course they wanted to preserve all that ice they could for cleanup.
And whenever there's an accident, political authorities quite rightly say, have we gotten this right? Sometimes they've said that accident was not so damaging, it was a rare event and we can live with it. Other times they've said this was unacceptable.
These were fairly serious incidents. They were international incidents. And we had to come to some grips that perhaps we needed to adjust our posture.
And so we recognized that, hey, there's a high consequence event that can happen here. It's unacceptable. We have to deal with it. Out of that came what we call the Wolski criteria.
Karl Wolski, assistant to the Secretary of Defense Atomic Energy, initiated a reappraisal of nuclear detonation safety in the wake of the 1966 Palomares accident. But the 1968 accident at the Thule Air Base in Greenland became a catalyst for change.
The Wolski criteria that was put out in 1968 gave 2 clear definitions of levels of safety for nuclear weapons. The key factor was, given an accident, the likelihood of a nuclear detonation should be less than 1 in a million.
And 1 in a billion for just sitting there, normal environments. Something that the U.S. public in Congress and in the White House would understand, so we put a number on the level of safety.
These accidents showed that you can have fire followed by crush, followed by electrical insult. A sequence of environments happening that you may at one time deem not to be credible, but nature has a way of voting.
Mother Nature's a devious adversary.
That's my personal view. Accidents are going to happen.
Given the accident, how will the hardware, how will the weapon system respond?
Will it go the way I say it will, predict it will, designed it will?
Versus a system that's highly complex where it would not always fail predictably. So given that, we have developed a set of design principles from which we implement nuclear safety from the start into the weapon system design.
In response to the 1968 Wolski criteria, all three AEC laboratories intensified their focus on safety. Los Alamos would introduce insensitive high explosives. Livermore would develop fire-resistant pit technology. And Sandia would establish the enduring concept of enhanced nuclear detonation safety. Underlying all of these developments was a new understanding, indeed acceptance, of the probability of an accident.
I think where we fool ourselves if we think we've thought of all the ways that accidents might occur. The key thing for weapon safety is, given the accident, prevent the ill.
The nuclear accidents of the 1960s shared common themes. They all exposed the weapon to extreme environmental insult, fire, crush, and electrical shock. By 1972, Sandia's Independent Safety Assessment Group would assemble evidence upsetting traditional understandings, findings that would forever shatter the image of order conveyed to the designer by circuit diagrams and layouts.
Creating an independent safety group, I think, was absolutely vital and probably the key to why improvements were made.
Jack Howard was strongly involved in encouraging an advanced development activity in a safety organization separate from the warhead developers.
If the design groups have somebody muttering constantly in their ear saying, always, shouldn't there be somebody muttering, never?
What we need is a simplifying notion. So a small group was convened, and I isolated them and said, I don't want you worrying about day-to-day problems. Think this through.
And so what I asked for Bill, well, we want to need some time, some months, to go in and really try to now understand safety from a more fundamental viewpoint.
In 1968, Sandia designers asked, are we doing what we need to be doing for abnormal environment safety? Their approach was twofold: analyze the safety features of existing weapons and expose those components to severe abnormal environments.
The feeling at the time was things are pretty good. We've had a lot of accidents. We've never had a detonation.
People didn't, at that time, understand much about accidents.
Well, I think early on they assumed that things could fail in such a way that the system wouldn't work.
Key assumptions at the time held that an electrical fault to ground will dud the weapon and that circuits and connectors will open up in an accident. Early detonation safety was achieved by employing ready-safe switches, environmental sensing devices like accelerometers, by using printed circuit boards and cable isolation to ensure the electrical integrity of the safety system.
And safety was really on isolating the wires from the power coming in to pre-arm the weapon, for example, from the charging circuits.
The early weapons were put together in such a way that this could all happen in the junction box. And in the junction box, you have the inputs and outputs together on a wiring board.
Wiring boards with all of these different paths in it, and then you maintain a separation between those paths, and then you put an insulative material, electrical insulation, over the top of it. You've made a cocoon around these items, and they're going to be safe.
But those were safety features in essentially normal environments.
All of this hardware was developed in a vintage when abnormal environment was not considered.
Once you start involving fire and unusual environments in that, then you start shorting out cables and coming up with circuits that can cause a degradation of the safety that you've built into the bomb.
After several years of intensive torturing of existing hardware, the study group found that the response was not predictable.
When test objects were subjected to thermal insult by an electrical fault, the charred organic material would cease to insulate and now conduct electrical current.
Conduction. And you can get conduction to many circuits in there.
In other words, you're creating new electrical paths within your wiring board, and those electrical paths could go through and arm the weapon system and fire it.
Charred insulation or melted solder would not simply open up a safety circuit and dud the weapon, but would cause unpredictable propagating damage. Further still, there was no technical basis for this model of safety practiced among designers.
Their assessment and their analysis was not based on fact, was not based on testing.
And this was a great eureka, if you will, in the safety arena, that we need an approach that allows for unpredictability.
When you really start to build a safe nuclear weapon, your first task should be to create a barrier system to isolate the critical power from your critical arming and firing circuit. So you need a barrier.
Barrierize those. And then you don't have to worry about what's happening outside.
It was a simplifying notion because now you didn't have to study all the ways things could go wrong, so it made the problem manageable.
In 1971, the Independent Safety Assessment Group proposed a radical redesign of all weapon electrical systems, beginning with the concept of an exclusion region,
where we isolate energy sources from critical nuclear weapon detonation elements to prevent a nuclear detonation. Exclusion barriers, which are walls that contain capacitor discharge units, are the energy sources that can light off the detonators for the system.
But you don't have an operational weapon. Make an operational weapon, then you've got to essentially put a hole in the barrier to put in the arming energy when you need it.
And we did this through what we call strong links, which are basically switching devices, so you keep this electrical energy off these elements like detonators.
We used 2 strong links. We were unwilling to assume that we had the skills necessary to devise a single switch that would give us 1 in a million protection.
Each one has to be independently effective to avoid some common mode failure. What you don't want is a common mode where, with the same kind of input, both devices would fail.
So we used 2 designed differently.
And then the third thing you had to do is to make sure your strong links were not susceptible to just common everyday voltages.
Some signal that would not normally be postulated during an accident.
An unambiguous indication of human intent is what it needs to open that gate.
That unique signal that was incompatible with all of the common voltages and the voltages as they may be modified by the abnormal environment.
Ultimately, the features of enhanced nuclear detonation safety were designed to prevent nuclear yield in the face of severe abnormal environments.
But eventually, everything